Okay, so this video is going to be on estimating limits. So the first thing you might want to ask is, well, what's a limit? A limit is a tool that we use in calculus to explore the behavior of a function near a point. And I'll explain what that means later in this lecture, and we'll look at it throughout the course. But before I do that, let me just give you the definition of a limit. So a limit as x approaches a, so that's how you read these symbols here. The limit as x approaches a of f of x is equal to L. And that's true if we can make the values of f of x as close to L as we like by choosing x sufficiently close to a on either side of a. So what does that mean? Well, let me illustrate this by looking at an example. So consider the function x cubed minus 1 over x minus 1. And we want to look at this function near the value x equals 1. Let me get a different pen color here, not the marker. Now naively, from algebra class, if we wanted to know the value of the function x cubed minus 1 over x minus 1 near x equals 1, we'd just plug 1 into that function. So we'd get 1 cubed minus 1 over 1 minus 1. And so naively, we'd end up with 0 over 0. But as we know from algebra, this is not a well-defined number. It doesn't tell us anything about the function. Furthermore, we actually know from algebra that since if we put 1 in here, we're going to be dividing by 0. 1 is not in the domain of this function. But it turns out that that doesn't mean that the function behaves in a crazy way near 1. And that's sort of why limits were invented, is we want to be able to say something about what the value of the function should be at a particular a, even if the function doesn't exist there, and based on the function's behavior. So let's look a little bit further at this example. And now we're going to calculate the limit as x approaches 1 of x cubed minus 1 over x minus 1. Now what does the definition say? It says we want to find a value that we get closer and closer to as x values get closer and closer to a, the value we're looking at. So this number is playing the part of a, this number is playing the part of x in the definition, and this is playing the part of f of x in our definition. Then we want to find L, if there is such a thing. So how do we do that? Well, we choose numbers that are close to 1, but not 1. So for example, we could choose 2. 2 is reasonably close to 1. We put 2 into the function, and we end up with 2 cubed, which is 8, minus 1, which is 7, over 2 minus 1. So we get 7 over 1, which is 7. We can certainly think of a number closer to 1 than 2, so maybe 1.5 is another good number. And if we do this calculation, we get 4.75. And of course, there's no reason to stop at 1.5. We want to get as close to L as we would like, and we want to choose x sufficiently close to a. Sufficiently close is sort of vague, but think of it as very close. So if we do this, we get, for x equals 1.1, we get 3.31, and for 1.01, we get 3.0301, and for 1.001, which we would think of as being pretty darn close to 1, we get 3.0030001. And notice, if I kind of go down this list, the x's are getting closer and closer to 1, and these numbers here are getting closer and closer. Well, it looks like they're getting closer and closer to 3, right? 7 is pretty far away, but all of these are 3, and they're decreasing as our x gets closer to 1, these values are getting closer and closer to 3. So we would like to say that the limit as x approaches 1 of x cubed minus 1 over x minus 1 is equal to 3, because as x gets closer to 1, the value of this function is getting closer and closer to 3. Now the definition says we can make it as close as we like. Well, what if we would like it closer? Right now we're off by about 3/1000ths. What if we wanted to be closer to 3? Maybe be off by a millionth or a billionth? Well, what can we do? Well, we can pick values that are closer, x values that are closer to 1. For instance, we could pick x as 1.000001, and if we put it into the function, we would get 3.000003. So we can pick values even closer to 1 if we like. And it's sort of a game. Whatever standard is set, you have to meet that standard by picking a value closer and closer to your a, or in this case to your 1. Now if you look back at the definition, there's a little clause here that says on either side of a. Since 1 was playing the part of a in the definition, what does that mean? Well, so far we've picked only values that are close to a but bigger than a. So really, to check this limit, we have to pick values that are close to 1 but less than 1. So here's a table of values. We have x and x cubed minus 1 over x minus 1. And if we pick 0, well, that's a number that's close to 1 but less than 1. And we put it in this function, we get 1. If we pick 0.5, that's closer to 1. It's still less than 1. We get 1.75. And if we pick 0.9 or 0.9, we get 2.71. And if we pick 0.99 or 0.99, we get 2.9701. Again, these values are, well, I should really write this over here. X is approaching 1. It's doing it now from the negative side. And these values, let me erase that, really are f of x seems to be approaching, well, it's getting closer and closer to 3. So that just cements our guess here. Now I should, in honesty, tell you that this is still just a guess. We haven't really calculated the limit at this point. We've estimated the limit using a table. There are ways you can formally calculate the limit. But we're going to start off by getting a nuts and bolts feel for estimating limits by choosing values on either side of the value we're interested in. So rather than take up all the fun for myself, right now take out a piece of paper and make a table of values to find the limit as x approaches 3 of the function, this very simple linear function, 2x plus 1. Remember what that means. You're going to choose x values larger than 3 but close to 3, and x values smaller than 3 but close to 3. Put them in a table, so organize your information, and then try and tell me what the limit is. Okay, hopefully you're done with that. And here's a table of values. So if we have x values here. I'll separate these into two tables, the ones larger than 3 and the ones smaller than 3. Well, 4 is a number that's bigger than 3, but close to 3, and if we put 4 in here we get 2 times 4 plus 1, which is 9. And we could choose, for example, something much closer to 3. How about 3.1 or 3.01? So for 3.1 we get 7.2, and here we get 7.02, and 3.001 is 7.002, and we have to choose values on the other side, so we could choose, for example, 2, and we get 5 here. We could choose 2.9. I have to do this in my head, so that's 6.8, 2.99, etc. And what you'll find is these are both getting closer and closer to 7 as your x gets closer to 3. Now you might at this point think that it's fairly trivial calculation and it's always going to work. Let me just leave you with a few thoughts. Actually, an exercise is consider the limit as x approaches 0 of, oops, got that backwards, of 3 over x. And I'll let you complete the table, but let me just throw some values at you. So x, if x is equal to 1, or 0.1, or 0.01, what happens? And how about if x is equal to minus 1, minus 0.1, or minus 0.01? What happens? Well, this is 3, 30, and 300. This is minus 3, minus 30, minus 300. What's the value for the limit? These numbers are definitely very close to 0, but these values are not anywhere near close to each other. In fact, they're getting further, the values are getting further and further apart. They're not leveling off. So in this case, the limit does not exist. And we'll talk about that in class.